Here we will look at molecules with 5 electron groups, or 5 pairs of electrons. The example in this case is phosphorus pentachloride, or PCl5. We see from the chemical formula that there's one phosphorus, which is in group 15, and therefore contributes 5 valence electrons to our molecule, and we have 5 chlorines, which being in group 17, contribute 7 electrons each. Adding our electrons together gives us a total of 40 valence electrons to distribute in our molecule. Now we will start by writing down the central atom, which in this case is phosphorus because it is the least electronegative of the atoms in phosphorus pentachloride. Next we will add the 5 chlorine atoms, which will surround the central atom, and then we will connect the atoms together with single bonds, giving us 2, 4, 6, 8, 10 electrons. Now the remaining electrons will be distributed as non-bonding electron pairs, giving us 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40 electrons. Now, this accounts for all the electrons in our molecule, and this is the correct Lewis structure for phosphorus pentachloride. The VSEPR class in this case will be AX5, where phosphorus represents the central atom A, and the 5 chlorine atoms surround the central atom, giving us the notation X5. Now we can see from our table that for 5 pairs of electrons, the electron geometry will be trigonal bipyramidal. And in this case, because we have no non-bonding electrons surrounding the central atom, the shape of the molecule is identical to the electron geometry, and therefore is also trigonal bipyramidal. And in this case, the bond angles between the atoms are 90 degrees and 120 degrees, respectively. The 5 electron group system has 2 different positions for the electron groups: axial, which is located above and below the plane, and equatorial, which is located entirely within the plane. The bond angle between the axial and the equatorial positions is 90 degrees, whereas the bond angle between the atoms located entirely within the equatorial plane is 120 degrees. And if lone pair electrons are present in the 5 electron group system, they will occupy the equatorial positions in order to minimize the repulsions between the atoms in the molecule. The next molecule we will look at with 5 electron groups is sulfur tetrafluoride, or SF4. So we see from the chemical formula that we have one sulfur, which is in group 16 and therefore has 6 valence electrons, and 4 fluorines, being in group 17, has 7 valence electrons each. Adding up our electrons, we get 34 valence electrons. Now, since sulfur is the least electronegative of the elements, it becomes the central atom. And then the fluorine atoms will therefore surround the sulfur. Next step is to join the atoms with single bonds, giving us 2, 4, 6, 8 valence electrons so far distributed. The remaining valence electrons we will distribute as non-bonding electrons, giving us 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. And of course, the last 2 electrons will be placed on the central atom, sulfur. So this is the correct Lewis structure for sulfur tetrafluoride. Now we see from the Lewis structure that the VSEPR class should be AX4E, where sulfur is the central atom. We have 4 fluorine atoms surrounding the central atom, giving us AX4, and we have 1 pair of non-bonding electrons, giving us the designation E. And we can see from the chart that for AX4E, the geometry of the electrons is trigonal bipyramidal, but because we have a lone pair, the shape of the molecule is dysphenoidal, which we see here. Again, the ideal bond angles are 90 and 120 degrees. In the case of sulfur tetrafluoride, SF4, we see that we can draw 2 possible structures for the placement of the lone pair electrons. The lone pair electrons can be either placed in the equatorial position or in the axial position. As it happens, the repulsions between the electrons are minimized when the lone pair electrons are placed in the equatorial position. And so this gives us the familiar dysphenoidal shape or seesaw shape for sulfur tetrafluoride. Next, we'll look at the VSEPR class AX3E2. And the representative molecule we will use is chlorine trifluoride. So first, we'll have to count the number of valence electrons in our molecule. And here we recognize that chlorine is in group 17 of the periodic table, and therefore should have 7 valence electrons. Likewise, fluorine is also in group 17 of the periodic table, so it should also have 7 valence electrons. But since we have 3 fluorine atoms, this gives us 3 times 7. Adding our electrons together gives us a total of 28 valence electrons to distribute in our molecule. Here we should recognize that chlorine is the least electronegative element, and therefore chlorine should be the central atom. And surrounding the chlorine, we'll therefore add our terminal atoms, which are the fluorines. Next, we'll connect the terminal atoms to the central atom with bonds, giving us 2, 4, 6 electrons distributed so far. The remaining electrons will then be distributed first on the terminal atoms. So here we have 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons distributed so far. Now the remaining atoms are distributed on the central atom, giving us 26, 28 electrons. And here we've distributed all of the electrons, and this is the correct Lewis structure for chlorine trifluoride. Since we have 3 atoms connected to the central atom, you'll notice that the VSEPR class is AX3, and since we have 2 pairs of lone pair electrons, we also have E2. So the VSEPR class is AX3E2. And this gives us an electron geometry that is trigonal bipyramidal, since we have 5 pairs of electrons. But since 2 of those electrons are in lone pairs, the shape of the molecule is T-shaped, and the bond angles are therefore 90 degrees and 180 degrees. For chlorine trifluoride, which has the VSEPR class AX3E2, we see that the lone pair electrons can be placed in either the equatorial positions or the axial positions, or a combination of both the equatorial and the axial positions. As it happens, the equatorial positions are the positions that are most favorable for the molecule, as it minimizes the repulsions between the electrons in the molecule. And as a consequence, the shape of chlorine trifluoride is T-shaped. Now it's important to remember that the presence of the lone pair electrons at the equatorial positions pushes back or repels the bonding electrons, and as a consequence, the bond angle between the chlorine and the fluorine atoms is less than the ideal angle of 180 degrees, and in actual fact, the experimentally observed bond angle is 175 degrees. For the next example, where we have molecules with 5 groups of electrons, we have the example of xenon difluoride, or XeF2. Here we have 1 xenon, which is in group 18, giving us 8 valence electrons. We have 2 fluorine atoms, which are in group 17, contributing 7 electrons each. Adding these together gives us a total of 22 electrons in our molecule. In this case, xenon is the least electronegative element, and therefore it is the central atom. This is surrounded by the 2 fluorine atoms, and we will therefore join these together with single bonds, giving us 4 electrons distributed so far. Now the remaining electrons we're going to distribute as non-bonding electron pairs. So here we have 6, 8, 10, 12, 14, 16 electrons, and the remaining electrons will be distributed as non-bonding electrons on the central atom, giving us 18, 20, 22 electrons. So these are all the electrons in our molecule, and this is the correct Lewis structure for xenon difluoride. We can see from the Lewis structure that the VSEPR class is AX2E3, where xenon is a central atom A, and the 2 fluorines are the 2 atoms surrounding the central atom, giving us the designation X2, and we have 3 non-bonding electron pairs, giving us a designation E3. In this case, we see that molecules with 5 groups of electrons have the electron geometry trigonal bipyramidal. But because of the presence of the non-bonding electrons, the shape of the molecule is linear. And here we can see a diagram showing the shape of the molecule, where the non-bonding electron pairs, 3 of them, are located along the equatorial axis.